All right, everyone, I am here in Vancouver at NeurIPS 2019, and I've got the pleasure of being seated with Josh Tobin. Josh is a former research scientist at OpenAI and a co-organizer of Full Stack Deep Learning. Josh, welcome to the TWIML AI podcast.
Thanks. Happy to be here.
Awesome. So let's maybe jump into a little bit of your background. You spent some time at OpenAI and you did your PhD at Berkeley, advised by Peter Abil, who's been on the podcast before.
Great. Yeah. So I got into the field about 4 years ago.
Okay.
Really, I started at Berkeley in the applied math program, and then, kind of on a whim, took a class with Professor Abil, who ended up becoming my advisor. And I was just kind of blown away by the potential of AI to make robotics work better. And so, through that, I ended up working with Peter and spending a bunch of time at OpenAI.
And so what are you currently up to?
Yeah, so I left OpenAI a few months ago.
Okay.
And I'm in the process of exploring kind of what to dive into next.
Figuring out what's next.
Yeah, exactly.
Nice. And so your talk here, actually later this afternoon, is on GeometryAware neural rendering.
That's right.
What's that? Is that something you worked on at OpenAI or kind of personal interests? Where
yeah,
does that come from?
So that's something I worked on at OpenAI, also through during my PhD at Berkeley, while I was spending time in both places.
Okay.
And so the kind of the core problem that I'm working on there is, how do we, in robotics, in order to act, robots need to first understand what's happening in the world. And so typically the way that you'll do that in robotics is you'll kind of take your sensor observations about the world and you'll map them to some way of representing the state of the world, right? Mm-hmm. So where are all the objects? What poses are they in? What configuration is the robot in, et cetera. But the challenge is that as you move to more and more complex scenes, then it becomes hard to write down a concrete representation of the state of the world. Mm-hmm. And so the focus of this work is on implicit scene understanding. So can we take some sensor observations about a scene and then use that to create a representation of the world that kind of implicitly has an understanding of what's happening in the scene?
Mm-hmm. And so can you be more concrete than that, or is there an example that you use to describe that?
Yeah, absolutely. Concretely, the way that you formulate the problem is you take one or more observations of the scene. So think about cameras imaging the same mm-hmm. scene from different viewpoints. And then you train a model, and the goal of that model is to, given some arbitrary other viewpoint, that could be any other viewpoint of the scene, the model's goal is to render what it thinks the scene looks like from that viewpoint. Mm-hmm.
And thus, if it can do that, then it has an accurate kind of implied or implicit representation of what's happening in the scene.
Yeah, that's the intuition, right? It's if the model can do that task well, it has to have some sort of representation internally that understands what's going on in the scene.
Practically, when you do this, how many cameras are we talking about?
Yeah, it's a handful. I mean, it's the formulation can really extend to any number. In practice, I usually used 3 cameras to image the scene, mm-hmm. and so then the fourth viewpoint is the one that the model is trying to predict.
That is the neural rendering part of the talk. Mm-hmm. GeometryAware implies that it's kind of a model-based approach.
In some sense, yeah. I mean, so the GeometryAware part is the inspiration for the work that I did and what I built on was this paper from DeepMind called GQN, Generative Query Networks.
Okay.
And so the extension that I added to that is the GeometryAware part. And so what it refers to is, if you know the geometry of the scene, so where the cameras are relative to one another, then that allows you to constrain the process of searching what pixels are most relevant to rendering a particular pixel. Mm-hmm. So if you're rendering a particular viewpoint and you want to know, okay, what should I image in this pixel somewhere in the image that I'm rendering? Then what you want to do is you want to go back and look at all of the images that you've been given as context and mm-hmm. sort of search over those images for relevant information. And if it turns out if you use the geometry of the scene, this thing from classical computer vision called the epipolar geometry, then you can constrain that search to a line in each of the context viewpoints.
And so maybe as context, kind of walk us through GQN and what that paper is talking about.
Yeah. So in GQN, they're taking this problem of neural rendering, right? So looking at a scene from multiple viewpoints and rendering from an arbitrary other viewpoint. And then they set up a model structure. And the way that model structure works is it's basically an encoder-decoder architecture. So the encoder takes each of the viewpoints and maps them through a convolutional neural network independently. And so then you get a representation for each of those viewpoints. Those representations are summed, and then you get sort of one representation for the entire scene. So that's kind of the encoder part.
Summed like element-wise or concatenated more?
Yeah, summed element-wise.
Okay.
Yeah. So then you take that representation for the scene, and you pass that to the decoder. And then the decoder's job is to take that representation and sort of go through this multi-step process of turning it into what it thinks the image from that viewpoint should look like.
Okay. And is there any particular intuition for the element-wise sum versus keeping everything around?
I think the main intuition is that you want it to be, you don't want it to depend on the order that you present the cameras in. So if you concatenate, then order matters. If you sum, then it doesn't.
Okay. And so their results were kind of purely based on this, just the camera angles and the kind of encoder-decoder architecture, and so that what you added was a constraint to the search space that is based on what we know about the geometry,
epipolar geometry.
Epipolar geometry.
Yeah. So basically, the contribution of our paper is, there's this sort of bottleneck in the GQN formulation where you've taken the encoder and that's given you a representation of the scene, and then you pass that to a decoder. But what we do instead is, instead of having this representation of the scene, instead we have an attention mechanism. And so that attention mechanism allows you to, when you're generating a new image, to attend over all the information in the representations of the context images that you've been given. And the way that attention mechanism works is by taking advantage of this sort of fact of 3D geometry called the epipolar geometry.
Is calling it an attention mechanism, is it like attention-like, or is it implemented the way attention is often implemented in these kinds of networks?
Yeah, so it's implemented exactly like kind of like a scaled dot product attention mechanism. But the way that you have to do that is, you have for every pixel, you're searching over a line, and so you need to sort of construct the right representation so that you can do attention in the normal way.
Okay, so you're kind of constructing a vector that represents this line that you're doing the dot product, and you're dot producting that with everything.
Exactly.
else.
Yeah.
Okay.
So for each pixel, we're constructing this vector that represents a line, and so when you aggregate all of those, right? So you have two spatial dimensions for the image, and then you have this line, and so you get this sort of 3D tensor, and then you're dot producting the image that you're trying to render, the current representation of that with this 3D tensor. And then that's kind of the attention mechanism.
Cool. And so tell us a little bit about the results of the paper. Is it kind of trying to get at, better accuracy in rendering the scene, or computational efficiency, all of the above?
Yeah, so
it strikes me that both of the above would follow from what you're doing.
Sure. Yeah, I mean, there's definitely data efficiency gains, but really the main goal was sort of coming back to the motivation for working on this. I primarily work in robotics, and so the reason I started working on this was to construct better representations for robotic scenes. And so the thing I really wanted to do was to extend GQN to more complex, more realistic scenes. So higher dimensional images, more like higher dimensional sort of robot morphologies, and more complex objects. And so the kind of main result of the paper is we introduced a few new data sets that capture some of those properties. And then we showed that our attention mechanism produces like kind of qualitatively and quantitatively much better results on those sort of newer, more complex data sets. The results are also better on the old data sets as well. But I think really the interesting thing is how much better they work on these newer data sets.
So tell us a little about the newer data sets and how they were constructed.
Yeah, so there's three new data sets. One is a data set that's based on the in-hand block manipulation work from OpenAI. And so it's,
related to the Rubik's Cube?
Yeah, sort of the precursor to the Rubik's Cube work.
Nice.
So before the Rubik's Cube work, there was the block manipulation work that was, I guess a little more than a year ago at this point. And so Yeah, we hadn't released the Rubik's Cube work yet at the time that I was working on this. So I worked on the older data set. And yeah, so you have a bunch of cameras looking at a robot hand that's holding a block, and the sort of colors of the cube in the background and the hand are randomized, and the hand and the cube can be in any pose. So that's one of the data sets.
Okay.
And so that's kind of meant to capture sort of what a quite realistic sort of robotic task could look like.
Right.
The second data set is what I call disco humanoid.
Okay.
And so this is like, the classic Mujoko humanoid model, but the poses of all the joints are completely randomized, and the colors of everything are randomized as well, and the lighting. So what it looks like is this sort of humanoid model that's like doing this like crazy jumping in the air dance moves.
Okay.
So that's kind of the second data set, and that's meant to capture, whether you can model robots that have complex internal states, right? So this high dimensional robot, and you need to model it in any pose.
Now, is the starting position randomized, or is it kind of randomized in time at every time step, or?
Yeah, so just one time step.
Okay.
So
it's just a single frame.
Yeah, a single frame, a single scene, and then multiple viewpoints of that scene.
Right. Got it. Okay.
But then each scene has different parameters for randomizing everything about the scene. So the humanoid is in a different pose. The colors and lighting are all different.
Okay. And so the third data set?
The third data set is, I think, the most challenging one. So it's basically a room, and then in that room are placed a few objects. But those objects are sampled from the ShapeNet object data set.
Okay.
So there's something like 60,000 possible object models. And so in each of the kind of million scenes that we generated, there's a different set of objects that are placed in that scene. And so it's really challenging because the model needs to understand how to render sort of essentially any type of object.
Interesting. At least in the first couple of those examples, maybe in the third, what kind of jumped out at me is not so much the complexity of the scene. Of course that's there, but also the attempts to randomize colors and things like that. I often refer back to one of Peter's videos of like the robot doing rope tying, and like it can figure it out on a green table, but then if you change the table to red, it totally fails. And so now, is a part of what you're doing explicitly trying to make the model more generalizable, or?
Yeah, I mean, so we didn't explore how generalizable the model could be in this work.
Okay.
But I think, a lot of my earlier work was on like this idea of domain randomization, right? So if you want to train a model in simulation that generalizes to the real world, kind of one of the most effective ways of doing that is to sort of massively randomize every aspect of the simulator. So
there's just some background that you brought into this task.
Exactly.
Okay.
Right? So I'm interested in realistic robotics tasks, and so to me, if you're working on realistic robotics tasks in simulation, you need to randomize everything.
Okay.
I think exciting future work could be to see how well these models transfer from simulation to the real world.
And so when you're evaluating the performance of these models, is it kind of like pixel-wise differences or distortions and error rates that you're kind of looking at, or what are the metrics that you're looking at?
Yeah, so the way that these, I sort of glossed over how the models are trained, but it's essentially like the easiest thing to compare it to is to a VAE. So you have a lower bound on the log likelihood, and
VAE, variational autoencoder.
That's right. Yeah. And so that's kind of the main way that you can compare the differences is by comparing the number of that lower bound. And then you can also look at things. We also look at things like L1 and L2 pixel-wise differences between the images, and so that's where our quantitative results come from.
It sounds like you have not applied this to real world. You didn't apply it to the Rubik's Cube robot or any robots.
Not yet. Not yet. Yeah.
Okay. Okay. So what are some of the other things that you're working on or have worked on or are interested in?
Yeah. So I think, as I mentioned, a lot, like the sort of big chunk of the early part of my PhD was working on domain randomization. So, really the sort of core question I got interested in early on when I started working in robotics is, if we believe that reinforcement learning is going to have a big impact in robotics, then sort of the main challenge is that most reinforcement learning methods are super data inefficient.
Right.
And so there's different ways that you could think about dealing with that. One is just to make reinforcement learning methods themselves more data efficient. So that's like a lot of work from Sergey Levine's group at Berkeley pushes in that direction. But I kind of became interested in this question of, can we just assume that our algorithms are always going to be data inefficient and then figure out how to generate data much more efficiently? So that kind of led me to work on simulation. The thing that I've realized recently is that I think domain randomization and other sim-to-real techniques work actually surprisingly well.
Other what techniques?
Other sim-to-real techniques. So transferring simulation to the real world, domain adaptation, and things like that. But so I think are still like very underexplored techniques in robotics. But the challenge, if you want to apply those techniques, has become that it's actually quite difficult to build physics simulators. And so in practice, that often becomes the bottleneck. Is you have some new robotics task you want to solve. Maybe you want to use sim-to-real to solve it, but then you have to go and do this manual process of constructing and randomizing the simulator that you use to generate the training data. And so that's kind of what started to get me interested in 3D scene understanding, is thinking about the question of, is it possible to automate part of that process, or at least to augment people in the process of creating synthetic training data sets?
Does that goal tie to the work we just talked about? What's the connection there?
Yeah.
Or are you not trying to say that?
I think it loosely ties to that goal.
Okay.
Right. So I think in my mind, sort of the end state for sim to real is you have like real to sim to real, right? So you collect some data in the real world, you use that data to generate a simulation, and that simulation is sort of richer than the real world. It's highly randomized. You train a model in that simulation, and you transfer that model back to the real world. Use that model to collect more data in the real world, and then feed it back into the simulation. Right. So I think you iterate over that process, and I think that if you have the right algorithms for that, then I think that process those types of algorithms will be really powerful. And so the main sort of missing piece there is going from a small amount of data about the real world, right? So a small number of observations about the scene that the robot is going to be interacting with, and then turning that into a simulation, right? And so this work on neural rendering is kind of, I think, like a conceptual cousin of that, because we're not directly trying to create a simulation, but we're trying to create a like sort of an implicit version of a simulation. And so right now it only captures 3D structure. It doesn't capture semantics or dynamics or anything like that. But I think it's kind of like an early step along that path.
What's the state of research in the real to sim part of that flow? Like, how far along are we?
Yeah, I think it's pretty early. There's been a number of papers that have come out on it, 2018, 2019.
What are the main things, the way that researchers are approaching the problem right now?
Yeah, I think so. I think like the general problem is very challenging. Right? So the general problem is inverse graphics, which is super, super hard to do. And so I think the main way that people are approaching the problem right now is to sort of create
inverse graphics, being like, I've got some set of images, create the representation.
Yeah, create a world that would generate those images.
Right.
And so I think like the main way that I've seen people approach this right now is instead of trying to solve the entire inverse graphics problem, instead sort of manually create a parameterized simulator. So a simulator that kind of, in principle, should capture the things about the real world that you care about, and then using the real data to optimize the parameters of that simulator.
Yeah.
And so then the hope would be at least you can use the real data to choose the distribution of parameters that allows you to best transfer your model from simulation to the real world. And so there's a bunch of work in that direction.
So for example, in the case of trying to use Grand Theft Auto as a simulator, take a picture of a road and try to generate something that looks like that road within the constraints of GT Auto.
Exactly.
Yeah. And so it sounds like folks are starting to kind of poke at that direction. How far, what do you have a sense, or do you know off the top of your head kind of some of the results that folks have seen there?
Yeah, I think I don't want to point to any specific results because I don't want to get them wrong. But let's see.
Or
where could you go to find this?
Qualitatively, like, are we at doing this with Grand Theft Auto, or are we more doing this with like simple rooms with shape library pictures, like how sophisticated are the simulation environments that we're even able to do this kind of thing with?
Yeah, I mean, so there are some results doing this kind of thing. I think like the primary results come out of NVIDIA doing this kind of thing with self-driving car data.
Okay.
And the results there seem to be promising. I think it's not clear to me how much effort still goes into the manual sort of creation of the parameterized simulation versus that being more automated. That's kind of the big question mark. I think also, although I'm not going to remember the specific papers off the top of my head, I wrote kind of a guide to sim to real transfer for robotics, and I cited a bunch of the kind of relevant work in this direction there. So I'm happy to share a link to that.
Yeah, please do, and we'll include it in the show notes.
Great.
You mentioned a few times domain randomization as a way to drive kind of generalizability and the more effective sim to real. Are you or other folks looking at more of, maybe kind of stretching the term too far, but like active learning type of approaches? Like, should the domains actually be randomized, or should they be, more carefully constructed so as to drive generalization?
Yeah, it's a great question. I think there's not really a simple answer to it. I think in a lot of cases, what I've found is that the simplest thing that you can do, which is just randomizing your simulation as much as possible, tends to give you like close to optimal results. So you might as well just do the simple thing. But for a lot of problems, that's not true. And I think like one of the main cases where that's not true is where randomizing your simulator too much actually hurts performance in simulation. Right. So, and if your performance in simulation gets worse, then your performance in real gets worse as well. And so I think in those types of cases, so that's like a lot of the dynamics randomization type stuff is an example of where that happens. And so in a lot of those cases, choosing not just randomizing everything, but choosing the right randomizations becomes super important. And so there's also some work in that direction. There's a paper from NVIDIA, for example, where they kind of do an iterative process where they, at each step in the iteration, they take real data and then they use that real data to optimize the parameters of the simulator so that the distribution of simulations is as similar as possible to the real data. They go back and collect more real data and then continue to iterate between those two things. So there's some work in that direction.
Yeah, you described the scenario where the simulator, you over-randomize and you drop performance in your sim. That seems like the easier of the problems relative to over-randomize. Your simulator does great, but you drop performance in real. Does that happen also?
I've not really seen that happen, right?
Okay.
I think usually more randomization tends to help generalization.
Okay, yeah.
Yeah, unless it hurts performance on the original task. It's in principle possible that could happen, but it's not something I've seen much in practice.
So I described earlier the GeometryAware approach that you presented as kind of a model-based or model-aware approach. Do you have ideas or other types of models that you might want to combine with a neural rendering that would help it?
Yeah, it's a good question. An interesting direction for this type of work is we right now model static scenes. So we're taking we're freezing a single time frame of a robotic task, and we're saying, can we understand what the scene would look like from another angle? But also super relevant is to look at entire tasks and try to compress those and understand those. And so what that would require you to do is also understand things like how objects interact with one another, how robots interact with objects, how physics works. And I think there are certainly other kind of concepts from physics that you could encode into a neural network architecture that would allow you to do those tasks more data efficiently.
Cool. Well, it sounds like really interesting work, and best of luck in the presentation.
Great. Thanks a lot. Yeah.
Do you want to kind of give a pitch for your next job or something like that while we're
No, I don't think so. I think people will just have to wait and see. Yeah.
Yeah. So it sounds like you've got something brewing.
Yeah, we could call it that. Yeah.
Yeah. Nice. Awesome. Well, Josh, thanks so much for taking some time to chat with us about what you're up to.
Yeah, thanks so much for having me.
Thanks.